Please welcome a program manager from DARPA's Information Innovation Office, Dr. Wade Shen.
All right, hello everyone. My name is Wade Shen. I'm the program manager for an effort called DataDriven Discovery of Models that I'm going to tell you a little bit about today. The premise behind this program is that we want to build automated machine learning systems that can automate the task of constructing models, munging data, extraction, transformation, load, cleaning, featurization, and so on. Because we have the problem today that every time we want to build a model, it requires a large set of data scientists to work iteratively on the construction of models. And generally, we have so many modeling problems that we want to solve that it's very hard for us to have enough data scientists to do all the things that we want to do. And so the D3M program is designed to figure out how we can do joint optimization of entire modeling pipelines from the early stages of raw data and how we gather that data to the end stages of learning and modeling of that data in order to be able to construct machine learning models that are optimal for a particular problem of interest. The hypothesis in the program is that we can do this automatically. We can do it with the help of subject matter experts who can guide the optimization process. And if we can do that together, we no longer need to have data scientists working on all of the different modeling problems that we care about all of the time. In other words, we can focus the effort of data scientists on complicated problems rather than having them work on the day-to-day mundane problems that they typically have to solve as part of their work. Now, the way that we do this is that we treat the problem of machine learning itself as a machine learning problem. So the key intuition in our program is that machine learning itself can be made into a machine learning problem and solved via machine learning. Now, that seems a little weird, so I think I should probably take you through why we think that's possible. But this process is generally called in machine learning research meta-learning. And the way that it works is essentially like this in cartoon form. We start with a series of modeling problems where we have data, and that data is associated with a set of potentially metadata about the data. And each of the data sets that we care about is then associated with a modeling solution. These modeling solutions are pipelines of processes that take raw data, convert that raw data into some modelable form, and then some series of machine learning steps that actually construct a machine learning model. Now, the key intuition here is that if the modeling solution is what you're trying to predict and the data is what you're trying to use to make that prediction, you have essentially the setup of a machine learning problem. And so what you can then do is use machine learning techniques to meta-learn how to construct modeling solutions for problems given data and labeled sets of data that are associated with modeling solutions. What this results in is what we call a meta-model. Now, a meta-model is useful in that it can take new sets of data, and given new sets of data, it can predict an appropriate modeling solution that we can then use to solve a new modeling problem that we previously haven't solved before. What that essentially allows us to do is to automate the entire process of constructing models. And if you think about that for a moment, this process, like all machine learning processes, can hypothesize many, many answers. And it can hypothesize many, many answers with different levels of confidence. And so what we would like to do is to make use of this scoring mechanism, this hypothesis mechanism, to then figure out how to optimize the process of constructing models end to end. And we do that by using meta-learning in conjunction with other techniques. So it turns out that doing meta-learning in and of itself arrives at good solutions, but you can do better by turning the problem of meta-learning into a meta-reinforcement learning problem as well. So imagine that we take a model that I showed you on something like the last slide, where we created that from ground truth. Well, it turns out that we can evaluate the model. And if we can evaluate the model, we can also iteratively figure out how to refine the model through an optimization process. And of course, because we're machine learning people, we do that through machine learning processes, specifically through reinforcement learning. So over the last couple of years, we've been working on turning the problem of modeling into, one, a meta-learning problem, and two, a meta-reinforcement learning problem, where we then optimize the models that get proposed by meta-learning systems using techniques akin to video game playing and the solutions that are used to solve chess problems. In fact, we actually borrow the concepts from Google's AlphaGo system and adopt them for the purposes of constructing these models, treating the construction of models as a game in and of itself. So does this work? It seems like it's kind of magic, right? So I basically said we can turn machine learning into a machine learning problem, and then we can solve it through meta-learning in a supervised way, and then we can further refine those models by doing reinforcement learning on top of meta-learning in this meta context, which is all very meta. Does meta actually result in something that's better? Well, it turns out it does. So one of the very preliminary experiments that we did when we first started this program was in constructing and rediscovering models for computer vision. So if you don't know what the CFAR 100 problem is, it's basically a computer vision problem. You're given an image. You need to identify whether that image is of one of 100 different possible classes of objects. So it's object recognition. And what we're showing you here are 3 different systems iteratively trying to get better at this problem of identifying objects from images. The blue dots here are one system with a whole bunch of randomizations through a process called genetic optimization. And you can see that genetic optimization eventually yields something that's pretty good, but not as good as the dotted line, which is what human beings can do through the process of iterative refinement of models, through graduate students working on this problem, through papers and so on. Over the course of many years, we've been able to achieve the dotted line that's shown to you here. But our green system is what we do in D3M. And what you can see is that the initial model that we construct just from meta-learning alone, which is the dot on the left side here, the green dot on the left side here, is already better than what we can do through genetic optimization. And then if we do further meta-reinforcement learning to further optimize the system, we can actually get better than human beings in terms of the performance that our model can achieve. It takes about 350 iterations to do that. And for this system to finally converge to a point where it gets its optimal performance takes around 1,500 iterations or so, and it's about 7,000 compute hours to construct this model. Now, that seems like a lot of compute hours, and it actually is, but it's actually much worse than that. So this problem of constructing this particular model, this model is actually a very small model relative to the large-scale image recognition models that we typically build. The training set is smaller than what we would typically use for building these models. And it still takes 7,000 hours, meaning that there's a very large compute complexity associated with this, because every time we want to do a step of reinforcement learning, we need to actually construct a model which involves doing the training again. And that process in and of itself is extremely expensive. So now we are working on ways to approximate that kind of process and do it much faster. But I thought what I would do is share with you some preliminary results from the program. So the program still has a long way to go before we're really able to replace data scientists. But we have some promising and tantalizing results coming from our program, which I think are worth sharing with you. The first of these is that it's not just that we can do these kinds of problems, build these kinds of models in problems like computer vision. It turns out we've been testing over the course of the last couple of years on a wide range of problems. And in fact, generally it is the case that our systems can beat expert baselines using fully automated techniques. And on average, we can beat these expert baselines by about 12%. Now, what's much more interesting is not just that we can beat expert baselines, meaning that we can beat data scientists constructing models manually on these classes of problems. It turns out that these systems can work with human beings. And so what we have done recently are a set of experiments where we evaluate the human being, a subject matter expert, a non-statistician, a non-machine learning expert working with our systems. to guide those automated systems in terms of the kinds of models that are plausible and the kinds of models that they should be exploring. And these humans plus our automated system can both outperform automated systems and outperform expert baselines, suggesting that the use of these kinds of automated systems in conjunction with people who have intuitions about how the underlying processes being modeled are actually working can actually make for better models than using statisticians who may or may not have subject matter expertise in a particular area. That, I think, is a very interesting result, because what it suggests is that the right kind of expertise to be leveraging here is expertise about the underlying process, subject matter expertise, and that many of the processes of exploration and modeling can be automated and can be worked with these kinds of subject matter expertise in such a way that you can come up with more optimal solutions. Now, you might ask, how can that possibly work? These automated systems are doing things that are way too complicated for humans to understand. And that's true in general. And you've heard talks now about explainability in AI and the general problem of how human beings need to communicate with machines and vice versa. But I thought what I would do is show you one of the systems that we've been building that tries to interface between humans and machines in a seamless way, allowing human beings to express the kinds of things that they know intuitively without bothering human beings with details of modeling that they can't understand. So this is a system that's built by the folks at Uncharted Software. They are one of a number of teams in our third technical area that work on what we call human-model interaction. And they've been thinking about this problem of how do I get subject matter experts to work with data and work with models and work with modeling systems to construct models, even though those users may or may not understand fully the underlying modeling processes. So what we're going to do is actually build an application. This application is an application that models the causal relations behind delays at O'Hare Airport. I'm sure many of you have flown through O'Hare and experienced this problem and would like to know why and generally don't. So we're going to try to tell you why it is that your flight was delayed at O'Hare. So the problem starts like, the process starts like this. We start by telling the system what we are trying to do. And this is called target selection in this particular user interface. And what you see here is that the user has expressed to the system that he is interested in modeling delays at O'Hare. And at the same time, our system is making suggestions to the user about what kind of data might be relevant for doing this kind of modeling. So for instance, transportation statistics, weather, airline data, and so on. The user then makes a decision about the kinds of data he or she wants to use. And then the system starts helping the user to propose models through the process that I'm going to show you here on the next screen. So the first thing is that the system shows you what you're trying to model, i.e. the target variable of interest. And it then recommends to a user a series of potential modeling variables that might be related to this particular target variable of interest. Through correlations. So the idea here is that there might be some causal component to the relationship between the variables shown under the correlations title and the target variable of interest. And the user can simply drag variables of interest onto the left side of the screen. And what the system does implicitly under the hood, beneath each of these arrows, is it constructs a model of how that variable might relate to the target variable of interest without ever exposing the user to the underlying modeling steps that are at play. So automated machine learning steps are at play, but they're only shown in the sense of the dependency of these variables between each other. Now you'll notice that when the user dragged the second variable over and said, hey, I think that aircraft delays are causing national air system delays at O'Hare, which is the second variable on the left side, what happened was that the system said, actually, I can't find a model here that tells me that that's true. And probably there's something wrong with this kind of dependency relationship that you're building when you're constructing this model. And so this alert is raised, again, through an automated process that's trying to predict whether or not a model could be constructed using this set of dependencies and the relationships between them. Now, what the user can then do is quickly make modifications. So in this case, the user can drag a factor or a variable into a position where it is independent of the variable that it used to be dependent on. And what happens is that the system then reconstructs a model, reevaluates that model, and in this case actually generates new insights about whether or not that model is good and a better outcome, suggesting to the user that this is probably a reasonable configuration of variables that might be modeling the underlying target variable. Now, the key thing to notice here is that this process is entirely seamless. You didn't see anything that looked like automated model search, right? What we've shown you is an outcome, namely the change of these orange lines and the relative change between the orange lines and the gray lines in the target variable selection slot. And what we've shown you is these arrows changing from a position where they're illegal or possibly errorful to a position where they are plausible. And so what the system is doing is allowing users to express their constraints on the underlying automated model construction system without having to have the user be exposed to all of the grotty details of how to actually make a model. Now, this is in fact how our systems can make use of subject matter expertise without having to have a great deal of modeling expertise. I think it's also worth noting that at least in the first phase of our program, we have been working on problems where the data sets are very curated and catered. Specifically, the modeling solution that we're asking people and machines to build sits somewhere in the subset of the data that we have given to the modeling systems, the automated modeling systems, or to the users when they're constructing these models. But the problem is the real world is way more complicated than that. In the real world, we almost never start with exactly the subset of data that we need to use in order to construct a model. Part of the process of building a model is actually discovering what data matters, finding new data that might matter for a particular problem that you didn't consider up front when you were devising a modeling solution and starting to work on an underlying problem. And so in the second phase of our program, we are now working on a series of problems where the data is underspecified, where the subset of data that we start with is not the set of data that we need in order to actually construct a model. And we're building systems that can autonomously find the rest of the data that's needed in order to complete the set of data that is needed to construct a model. And to do that, we're building a resource called DataMart. You should think about DataMart as an autonomous data gathering and data discovery resource that allows machine learning systems and data scientists to quickly find and automatically find augmentations of the data that they have in order to construct really high-quality models. The way that the DataMart works is by discovering huge resources online of data sources that people have posted. So as you may know, our government, many governments across the world, many organizations across the world publish data. They publish data that they've gathered through for experimental reasons. They publish data that they gather because of surveys and other things that they do, economic indicators. But often it's very hard to figure out how to get that data into a form that's modelable, to discover that it's there, to actually discover that it's related to a particular modeling problem. So what we are doing is building a resource that looks a lot like a search index for data. So think about something like a Google index for data that is not only queryable by data scientists, by some kind of semantics of the data that they need, but also by data itself. So if you have some set of data, what other data might be related to the data that you have on hand? How do we find that based on the statistics of the data that you have and the statistics of the data that are out there? This is the kind of thing that DataMart is designed to help you do in an automated way. Now, the promise is that by the end of the second phase of our program, we'll be able to start augmenting data automatically for problems that are underspecified. And that actually tries to fully address the class of hard problems that we now have in applied machine learning and data science. So with that, I will end the talk here today, but I invite you to ask me questions about this, because I know that when I talk about meta learning and machine learning for machine learning, that it can be a complicated and confusing topic. But the promise of these techniques is that they can automate the process of data science, automate the process of constructing machine learning models. And while it seems like magic, it actually is true that we can do these kinds of things. Thank you. Okay, so it looks like I already have questions, so I'm going to answer a couple of these questions for you guys. The first question I have here is, do you see meta-learning as a viable opportunity for the military to use in optimal, automated, adaptive, and intuitive decision-making in the operational realm? Well, I think that is actually the kinds of use cases that we have in mind. It turns out that a lot of military decision-making, a lot of decision-making in general, should be data-driven, right? We should make those decisions based on what kinds of potential impacts they might have on the world. But building a model of those kinds of potential impacts is often so hard that we don't make those kinds of decisions in a data-driven way. If we have a mechanism for building models automatically or semi-automatically, effectively making that process near free, then we can start talking about doing decision-making that's very data-driven all the time. And that is kind of the driver for a lot of the work that we do in D3M. Make models available everywhere, make it cheap to construct those models, make it possible to do that kind of decision-making effectively in a data-driven way. A second question here. What are the domains of focus in the program? An environment of a robot, question mark? What domains are amenable to this kind of approach, and what domains are not being developed? So we've tried to be very general. So I showed you a small subset of the problems that we use for evaluation purposes. So you saw computer vision, you saw medical problems, baseball prediction, a bunch of other things like that. The reason is that we want to have problems that are very general, because we think that this kind of machine learning for machine learning can be applied very widely. So every year we've actually been conducting evaluations on somewhere between 50 to 200 problems. We've been working on with a number of transition partners who have real operational problems, from things like precision agriculture to military applications. And that wide range of problems allows us to figure out what the limits of these kinds of techniques are. So far, we haven't come across problems where we can't do anything. There are certainly problems, as I showed you, where we are not as good as experts yet, and it'll require further tuning before we can get there. But I think that the problems themselves, or the kinds of techniques that we're building here, are extremely general. A third question here. How are you getting feedback when you develop your systems? Well, there are a couple ways that we can actually get feedback. One is that we can work on a lot of problems. So we've curated a huge set of test problems for our automated systems to work on. And then every year we also run a series of user evaluations where we bring subject matter experts in to use our systems. And pretty soon we'll also be bringing data scientists in to use our system to measure whether or not we can actually make them more efficient at solving problems. But part of the DARPA MO is to have formal evaluations where we can have measurable outcomes associated with everything that we do, including when we're trying to do user improvement. And so that is actually how we do that on a yearly basis. And lastly, I have a question here. How can we reduce the computational complexity of model discovery? So I hinted at this problem of model discovery being very, very computationally intensive. But there's also a whole bunch of tricks that are not employed in that chart where I showed you that it took 7,000 hours for us to beat human beings at constructing computer vision classifiers that were not yet employed. And a number of techniques in approximation of models, so not training a full model, partially training a model, stopping the training of models early, approximating the architecture of a model with a simpler model, with a proxy model. These are the kinds of things that we can do to make this process faster. We actually have preliminary experiments that suggest that that 7,000 hours can be reduced to less than an hour. When you can reduce it to less than an hour, then a whole bunch of real problems become plausibly solvable, with a limited amount of compute power. OK, if you have any other questions, feel free to ask me offline. I'll be around all day, so just come out and reach to me. Thank you all.